In this video, we will practice doing AP-style multiple choice questions relating to polynomial functions. This is AP Precalculus, topic 1.4. If you appreciate the channel, don't forget to hit that like button. Number 1, for the polynomial function g, the rate of change of g is increasing for the interval less than 2 and decreasing for the interval greater than 2. Which of the following must be true? Notice that we are talking about the rate of change of function g. A common mistake would be to think that we are saying that function g itself is increasing and then decreasing. That would mean we definitely have a relative max at x equals 2. I want you to memorize this chart showing the graphical relationships between f, the rate of change, and the rate of change of the rate of change. On your next quiz or test, you should write this chart on a piece of scratch paper and use it to help you throughout the assessment. For this problem, they are telling us that the rate of change is going from increasing to decreasing. That means the function itself goes from concave up to concave down. And where a function goes from concave up to concave down, that's called a point of inflection. So the graph of g definitely has a point of inflection at x equals 2. And because the rate of change was increasing before x equals 2 and then decreasing after x equals 2, then specifically the graph is concave up and then concave down. So the answer is D. Number 2, the polynomial function f is given by f of x equals x minus 2 times 3x minus 1 squared. Which of the following descriptions of f is true? The leading term of a polynomial tells us the degree and the leading coefficient. When you have a polynomial that's given to you in factored form like this, you can find the leading term by ignoring the constant. So the leading term can be found by multiplying x times 3x to the second power. So this is the same thing as x times 9x squared, which would be equivalent to 9x to the third power. So the leading coefficient is 9 and the degree is 3. So let's see, degree 3, leading coefficient of 9, the answer is D. Number 3, values of the polynomial function f for selected values of x are given in the table. If all the zeros of the function f are given in the table, which of the following must be true? The zeros of a function are the x-intercepts of the function. So we know that f of x will touch the x-axis here and here. In addition, we have these 3 other points. The problem says that 1 and 5 are the only zeros of the function, the only real zeros, so we can sketch a reasonable graph of f of x. F of x will look something like this. Let's see if this is enough information to eliminate all but one answer. The function f has a local minimum at -1, -36. No, this point cannot be a local minimum, so the answer is not A. The function has a local minimum at 5, 0. That's possible. The function has a local maximum at 3, 4. That is also possible. The function has a local maximum at 1, 0. That is not possible. We can throw that out. So we've narrowed it down to B or C. To choose between B or C, we need to read very carefully. It says in the directions, which of the following must be true? Only one of these has to be true. Does the function have to have a local minimum at 5, 0, or does f have to have a local maximum at 3, 4? Let's go back to just dots. Keep in mind that 1 and 5 are the only zeros of function f. is there a way that I could draw the curve such that 3, 4 is not a relative max? Sure, there's nothing that tells us that f doesn't go up higher than 4 and then come back down through the point 3, 4. So option C does not have to be true. On the other hand, there is no way to draw f so that 5, 0 is not a local minimum. For example, if I try to draw f going lower than 5, 0 so that this will not be a relative min, well, the only way that would happen is if we had another 0 somewhere in here. And we are told in the directions that these are the only 2 zeros. So this is not possible. Therefore, the answer is B. Number 4. The graph of the polynomial function g is shown. The function f is defined for the interval from 0 to 3 and is identical to function g on that interval. How many total local minima and local maxima does the function f have? So function f is identical to function g, except it begins at 0 and ends at 3. So focus on the green, and that is f of x. How many local minima or local maxima does this have? At first glance, it's tempting to say 2, because obviously we have a relative max here and a relative min here. But is that all? No, the or equal to symbols on this interval tell us that the endpoints are included. And this endpoint on the left counts as a local min, and this endpoint on the right counts as a local max. So the answer is B. Number 5, the polynomial function f is given by f of x equals, well, all of this, where a does not equal 0. And b, c, d, and k are constants. Which of the following statements about f is true? Looking at the leading term, we see that f of x has degree 4. That's an even degree. Even degree polynomials have the same end behavior on the left and the right. So either it's rising on the left and rising on the right, like both of these, or it's falling on the left and falling on the right, like these. If the polynomial is rising on both sides, like these, there's going to be a global min somewhere, but no global max. If the polynomial is falling on both sides, like these, there's going to be a global max somewhere, but no global min. So we can see that there's going to be one or the other, global max or global min, but not both. So the answer is B. F has either a global max or a global min, but not both. Number 6, the graph of the polynomial function f is shown. How many points of inflection does the graph of f have on the given portion of the graph? Remember, a point of inflection is where a graph changes from concave down to concave up, or from concave up to concave down. From left to right, f starts out concave down. At some point, it switches to concave up, so there's going to be a point of inflection in there somewhere. Then it becomes concave down again, so there must be a point of inflection in here somewhere. And then later it becomes concave up one more time. So there must be a third point of inflection somewhere in here. So the answer is B. Hey guys, don't forget to like and subscribe, but also if you found this video helpful, there's a lot more where that came from. You can click the upper link, which will take you to the whole unit playlist, or you can click the lower link, which will take you to the next video in the playlist. See you there.